propose an explanation for origin. So graphene is a honeycomb structure carbon atom where 3 electrons are coupled in bond. The fourth one, in orbital normal to the plane, is hop. And by considering hopping to the neighboring lattice A and B, and by considering hopping in a time binding model, one can find that the dispersion relations which are basically modular transfer of the hop. And the important result here is that complex bands and they touch at the gate point at the corner of the room. So, analogous hopping problem in the case of magnet is when one has ferromagnet on the Honeycomb lattice, time a split. So that's a Z-1 of boson can hop, and the equivalent the electron now the XY part of the Heisenberg. Okay, but fundamentally the problem is identical, except that we have a fine structure lifted up in energy because these are bosons, so we can't have a final station of the bedroom. So the magnetic bracket is gamma point, then we have an acoustic Magnon branch, then an optic Magnon branch, and they touch at the corners. And so here we have the Dirac horns that initially start at constant energy in the circle, but really symmetry wise, only. One is today. I forgot about this. So it depends on the energy field in the. It's coming. So this is probably 8 MeV. 8 MeV, yes. So we have nodal points at the corners of the point. This is at a finite energy because it's both. But fundamentally, the same kind of symmetry protection first here. So, it's probably interesting to understand the degeneracy in terms of spin arrangement. So, for a spin wave, we think of spin waves as harmonic protection around the ordered spin direction. So, here's a illustration of spin wave propagation horizontally, where looking above the projection of the tilted spin vertical axis, preset is bounded. So we support the dispersion relations along the direction that greatly out from. How would I know that? Can I speak closer to the laptop maybe, or? Is it better now? Yes. Okay. Sorry. Yeah. Okay. Well, from here. Yeah. Okay. So here are the two Magnon branches. The acoustic branch, the optic branch, where the two sublattices in the phase in the opposite. Then once we reach the corner of the Brillouin zone, this equation a third, then focusing just on one side, are all at 100. So now consider the situation of spin B. If it's acoustic mode, so this blue mode up here, it's in phase with A, so it's pointing down in projection. However, because these three A spins all make a 120 degrees angle, then there's no net in-plane mean field that would fix the orientation of B. So whether this points down or up, it's exactly the same energy. So that's essentially the origin of the degeneracy at this particular point. The acoustic and optic modes have the same energy. So not specific to the Heisenberg model. In fact, this symmetry protected degeneracy occurs for a wide range of models. It occurs, for example, for the Ising XXZ model, where we have easy axis spins pointing out of the plane. It occurs for easy plane XXZ model, where spins are in the plane. It also occurs if we have a more general type of interactions, where the interaction along the point and perpendicular and also along Z are different, so X, Y, Z type interactions. However, one can open a gap in special circumstances, for example, by adding Jaroszewski-Murray interaction on next nearest neighbor bond. And this is symmetry allowed because there's no inversion center halfway along this red bond up here, for example. For example, for the case of an Ising XXZ model where spins are out of the plane, and so this Jaroszewski-Murray vector that's out of the plane is along the quantization direction, then the DM vector acts as a complex hopping for the magnons, and this introduces a gap at this point at the corners of the Brillouin zone. However, the presence of DM itself is not sufficient to generate a gap. For example, if we have an easy plane XXZ model, so spins are in the plane, then the DM vector cancels and has no effect on the hopping of the magnons, because by threefold symmetry, this red bond here is the same as the horizontal one up here and the one there. However, by mirror imaging, this DM vector has to change sign between the red and blue bonds, and so the effect of all the 6 interactions cancels out. So the main message here is that these nodal points can be very robust, and only under very special circumstances one can open up a gap. They're also robust if one, this is not fundamental 2D physics, but it's also robust when we add interactions between the layers. In this case, the nodal points form nodal lines, and depending on details of the interactions, they can be just straight up going along C star, or can have some winding or modulation depending on details of the interaction. So the material that I'm going to talk about has these stacked layers and has nodal lines along the TI. I mean, these are very different. They will be very different. This in the Heisenberg Dirac model are nearby for the transition out of the ferromagnet is quite far away. Please, yes. Uh-huh. Right. Yes. Yes. Yeah, so people talk about the parity times time reversal symmetry being the symmetry that protects the Dirac points so there will be a symmetry. There are situations where you can have non-symmetric symmetries, like time reversal times glide, also protecting some of the nodal points or nodal lines. There's always a symmetry protection. As far as I understand, there's different mechanisms. So in the single layer ferromagnetic honeycomb, my understanding is that it's parity time reversal, but there's more complicated systems. Here for the hyper honeycomb, or sublattice problem, where some of these nodal lines are connected by time reversal times the glide. Okay, but maybe theorists in the audience could on this. That's my limited understanding of this aspect. Hey, Yankee, are you happy with the statement I made? Very much. Vanadium iodide. Yeah. Yes, I think there's discussion about okay. So probably worth is very strongly heightened. Actually, the measurement to determine the presence of a gap requires very narrow size. So if the size that you integrate wide, and also having finite crystal mosaic, everything out. So in the most recent measurements on chromium bromide, there's no gap. The lead person allows sort of mathematical problem to the Zeeman formula, where there is a virtual radial magnetic proportional delta K, the part of nodal point, in the isospin sigma, which is pointing along K, so away from the point in the top band and pointing in for the bottom band. And that gives a natural explanation of the spectrum, which is linear in momentum. So this isospin is quantum number from the actual spin was both magnons adopted corresponds to delta SZ along the quantization direction -1. This is an isospin which really characterizes the wave function decomposition on the p sublattice. And there is isospin can directly manifested dynamical structure factor because this one can show that is proportional to the projection of the radial wave vector away from the zone center for the projection of the isospin on this radial. So if we look logically, one projection as a color on the Dirac cones, then the strict position here, which is away from the zone center, where the isospin is along the radial wave vector, this will be high intensity. But if we go in 180 degrees on the other side, they're in opposite phase of the intensity count. That's exactly in anti-phase of the bottom band where the isospin moves in. So there are very strong intensity modulations that are expected. So part of our motivation was to see the experimental manifestation of this band crossing and reveal this strong intensity modulation. So as was alluded before, you can't really see the here. I don't know, is there any way to, oh yes, I can move this. Fine. Yeah. So the magnon bands very thin, they can be manipulated by magnetic. And so you could imagine situations where you manipulate the bands enough such that you actually move the positions of the wire nodes. And this has been predicted, for example, of the Heisenberg ferromagnetic pyroflow, where we have a four-type problem here. And there are plastic bands and similar bands at the top, but in the presence of interaction, actually the bands sit here and there are two wire nodes opposite topological charge. And the prediction here is that the ground ferromagnetic polarization is not fixed by the model. So, but you can fix it with a magnetic field, and the wire nodes occur along the direction of the field. You can imagine experiments where you rotate the direction of the magnetic field, the wire nodes follow with you. Other situations that might be of interest is where the magnetic field changes, shifts the bands in energy, and nodal points can appear or disappear to have sort of topological. Are the possibility of having higher order nodal lines, for example, as I mentioned in this four sublattice hyper honeycomb structure, which is a generalization of the honeycomb structure but with bond rotation that makes it three-dimensional. Here one can have a situation where four bands meet. So one can have higher degeneracy points, and also there's issues about what terms lift this degeneracy, and so on. And one may also be interested in what happens to the temperature when you put temperature in and you have quasi-particle scattering, whether the damping is the same at the nodal point as opposed to points away, and so on. So today I'm going to talk about the experimental manifestation of these nodal points in a relatively simple system. Cobalt magnet. So here, the basic building blocks are cobalt of Diffraction, and there's an edge here in the middle, with a void in the middle. And the crystal structure is such that there's perfect three-fold symmetry at each side, but these are compressed, so the octahedra are not used but have a trigon. And these are stacked up, not right on top of each other, but with some offset. But the vertical stacking actually doesn't increase the number of sublattices. So we still have two cobalts for primitive. Normally, this can be described by a rhombohedral cell, but we're going to use the hexagonal notation with a large parameter and 3 layers per unit cell. So here I'm showing some neutron powder diffraction measurements that we've done to confirm the magnetic structure model, which is the ferromagnetic order of movement in the plane with anti-ferromagnetic tracking. That leads to a doubling of the unit cell, new magnetic tracking. And this can be fitted extremely well. Model. And in addition, we extract the magnitude of the ordered moment, magnetons, supporting constraint on our. So one can also see these magnetic fields diffraction measurements. Here's a picture of a sample that we've had for inelastic neutron measurement, and here is the zero energy transfer along the direction of the in the AV plane, if you like. So these red spots correspond to magnetic backticks, and the fact that they occur every 3 Boolean zones is associated with this 3-layer stack. And nice order parameter indicating a continuous transition to the same temperature as the powder, and also where susceptibility has an anomaly, and where other people have also seen anomalies. So we're confident about the high quality of the single crystals. So a little bit about the origin of magnetism here. So we have cobalt ion. So at the ion level, we have an orbital angular level, it's a Kramer's ion. So we have an L equals to 3, 7-fold degenerate, and the presence of, if we put these ions in a cubic octahedral environment, lifts orbital degeneracy with the lower triplet and some other triplet and singlet higher up. And then this triplet can be described as an effective L equals to 1. When that's combined with the spin, we get a J effective moment, which has with the lowest level a half and 3 halves and so on. And then by applying the trigonal distortion, which happens from lattice, we're away from cubic symmetry, and we expect a splitting of this a half to J 3 half exciton. And in there's experimental evidence for that. These peaks here, the blue and red, we associate with transition to the trigonally split J3 half level. So just to put things in perspective, at low energies, because of exchange, we have ordering inside the lower doublet, but then and then we see magnons, but then we also see transition to these crystal free levels, if you like, and the transition, the exciton from J half to J3 half, even this one is dispersive, which indicates that in this system we have the unusual situation that magnetic exchange, crystal field splitting, and spinel recoupling are somewhat comparable. This is a relevant data. So we look at the neutron spectrum using time of flight neutron scattering. So ISIS, where protons are accelerated very close to light, and then proton beam is directed to the target, and every proton excites a nucleus and emits out about 20 neutrons. These are then guided towards spectrometers. These days, you have an instrument with 90,000 detectors that count neutrons at the same time. And so we have the degrees of freedom for the detector and the time, which is referred to energy. So neutrons that arrive slower have transferred some energy. And then by rotating the crystal, that's the degree of freedom. So we can obtain intensity maps as a function of the HKL and energy. And so that's what I'm going to show now. Okay, right. So I wanted these data sets where in the center of the image, magnetic practice, long range ordering. And so what we see is a very sharp, soft mode, very intense around the practice, and the weaker intensity of that. That's sort of reminiscent of systems with easy plane anisotropy, where very intense mode corresponds to fluctuations in the plane. The other mode corresponds to fluctuations out of. If we look with high resolution and low energy, we need a gap that I'll describe later. But for now, I want to focus on these intermediate energies, where here we have a gate point, as indicated in this diagram. So what's unusual here is that the other positions are exactly the same point, but they are approached from different directions in the plane. So, and you can see that in one case, one mode is completely absent, in another case, both are visible. So, if we now do a constant energy slice that's just above nodal point, all the intensity. So, if we tap transversely to the radial direction, then we clearly see both modes crossing at the case. However, if we go along the radial direction, the center line up here, one mode is entirely. This corresponds to if we were to plot here the theoretical predicted intensity modulation, then this scan to the right here corresponds exactly to seeing the spread modes here down and spread modes up, and the black modes are absent. Whereas the orthogonal direction scan up here is both of them. So one can reveal this intensity modulation by picking up a constant energy and plotting the intensity. So, so we get a constant energy and plot the intensity function triangle out. Here, the solid points correspond to the intensity in the top band, and empty points correspond to the intensity in the bottom. As you see, there's a maximum minima that are 180 degrees away. They're exactly anti-phase between the top and the bottom band. It's a very non-trivial effect, because if one sums up the two, one gets a constant intensity. So this is associated with the particular type of untouched which thinks the wave function. So just to show you that this is a non-trivial effect, there are other dispersive points that we see in the perimaterial. For example, just above the Bragg peak, we have a gap, but then it's a conical dispersion above it. So if we do a constant energy slice up here, then the intensity is constant around it. So here it shows that the intensity is really the fact that it's very strongly modulated between the two with yeah, I can naturally understood in the picture. Isospin rotate through 360 as we go around the nodal point, and so the intensity. That's why we get cold. And something similar has been seen also. Again, one can think about the intensity here as due to interference scattering from the two sublattices. So now, of course, we have a 3D system here. So we can do this experiment against L for any L value. So because we have another line. So if we go L equals 0, it means that we treat all the levels, all the layers equivalent along the lane. And the intensity maximum and minima are exactly along the radial direction. Here is minus 60, 20, or that's exactly as expected for a single honeycomb layer. However, so in positive now, there's a net shift to one side. Negative now, there's a net shift on the other side. And this is a real effect. It satisfies divergence prediction of the lattice, which means that scattering here is rotating in the opposite direction, scattering the other case one, and so on. So, and this is to understand this because of the buckling of the honeycomb. So this originates from the crystal structure. So as I mentioned before, we have stacking of cobalt honeycombs. In between them, there's a titanium honeycomb shown here in light blue, and the stacking is offset. For example, this cobalt up here is above a void, and this cobalt up here is above a site. So, so the sites that are above voids will push themselves into the voids, and the sites that are above atoms will push themselves up. So there's an alternation in position as we go along the honeycomb, and this can be captured by adding a phase factor with the component in the hopping term, and this gives rise to an interference that depends on L, and in fact has a periodicity that depends on the position of the two atoms, and in this case we would have to go to L equals 20 or so to really recover the periodicity. And the magnitude of the offset and the sign and all the symmetry well captured, so we believe this is the right picture. So in some sense, coloring of the cone actually rotates around as you move up along the z-axis. So this is the sort of the 3D effect that's different from graphene. So more now about how we extract Magnon dispersion. In order to get so from the 40-dimensional data, we extract dispersion of several directions on equivalent directions brilliantly. And then we map back to the antiferromagnetic zone, and we see very good consistency over many dispersion points that we extract. So how we determine the Hamiltonian? So the experimental data are indicated practice strong modes here. Now, if we start from the 2D Heisenberg ferromagnet, so that would have the touching points at the corners of brilliant that we see. However, the dispersion is quadratic. The ferromagnet conserves the spin. But we see a strongly linear dispersion. So if we make the system in plane, so an XY ferromagnet, then we recover the strong V shape of the dispersion as we see experiment. And now the next stage is now to add coupling between the layers with some interlayer dispersion. And we do that by assuming that all the couplings can be of easy plane form. And one thing that we have by hand in this parameterization is the presence of cap. I don't know, is there any way to get rid of this banner? Really a bit annoying, but anyway, let's put it there. So if we got my hand, constant to the Hamiltonian would essentially only modify the spectrum at low energies and will leave the rest essentially done. So we include the near stable coupling, which involves super exchange between cobalt, oxygen, cobalt, and then we also include all the paths that need a super exchange, cobalt, oxygen, oxygen, cobalt. And that we basic this notation. And then by doing that, we can obtain a very good parameterization of all the dispersion points. There are several thousand dispersion points here, and one can parameterize all the dispersions very well. So apart from the region which is the key point, which I'll come back later, one can obtain a very good parameterization. And dispersions for also the strong modes are strong, the weak modes are weak, the absent ones are absent. So we believe this parameterization captures very well the Magnon wave function. Now, there are, of course, I don't map this and one of them is the fact that we've had to put in the gap by in the easy plane excitation model. There's a continuous symmetry, and of course, we don't have that geometry with the gap. Then there are also other findings. Look along spectral direction along the zone boundary. For example, here between two nominal K points, if you like, the XXZ model predicts that the two lower modes are exactly degenerate, whereas experiment shows a clear separation. So this splitting cannot be explained. The fact that these are degenerate is really a symmetry of the XXZ model, which is not really in the real model. So we have to think of what are the terms or what are the effects we can include to explain these two aspects. Cobalt is a continuous ion, so the lowest doublet will be an effective spin-half. And we know that in that case, there can be no local anisotropy because all the anisotropies in terms of spin come up as polynomials of even order in spin. Because of property of Pauli matrices, the square of all the spin components is a constant irrespective of the actual wave function. So the important result here is that the preferential direction is selected by interaction, not selected by Now, of course, we've assumed a very simplified form of interaction, which the interaction matrix is diagonal, and the x and y parts are the same. Now, for the actual material, many other anisotropic terms are allowed because the middle of the nearest neighbor bond only has inversion symmetry. In principle, can have all the symmetric types of exchanges are allowed. So we'll first look at the most obvious anisotropy, which is the exchange difference components along the bond and perpendicular. So let's consider about the extreme case where the spins interact only along the bond direction. So these two would have an SY1, SY1 interaction, but these two would have SY2, SY2. Now, each one has a preferential direction for the orientation of the moment, but actually, if we add all three of them, that's a sum of 3 cosine squared with offset of 2 pi by 3, and the sum is independent of the angle pi. So the threefold symmetry of the lattice and the ferromagnetic order ensures that, in fact, one can show more formally that any symmetry allowed spin bilinear spin exchange cannot lift this independence of the energy as a function of angle. Even dipolar interactions cannot lift this dependence. So then one could pursue several scenarios. One can say that, well, the magnetic ordering is in fact breaking the symmetry from threefold inversion symmetry. So one can, if one has very strong magnetoelastic coupling, then one bond can become stronger than the other two, and then one doesn't have a independent constant here. However, experimentally, we see no evidence in diffraction of any difference between A and B, a very high accuracy. So the other possible mechanisms could be order by disorder, because of course this is a mean field calculation, but the crystal structure doesn't have symmetry; it has only discrete symmetries, and so one can think that the spin wave spectrum and the harmonic part of that, be a half h bar omega, would then depend on the spin orientation, and that could select potentially several directions for the moment plane. And the third possibility is to go beyond the lowest doublet approximation and include also orbital fluctuations. So let me describe order by disorder by quantum fluctuations first. So I'm going to assume that we have some anisotropy eta between the interactions along the bond and perpendicular. So if we calculate the Fourier spectrum and the harmonic part of the 0-point energies, that's a half h bar omega summed over all the modes over orbital and zone, then this quantum energy actually does have a dependence as a function of that. One does see 6 very well-defined minima associated with spin favoring to be along the bond or perpendicular to the bond, depending on the sign of the anisotropy. And one can extract the dependence of the this energy dependence function angle, and from that, once we have the energy landscape, so there will be an easy plane anisotropy that wants to spin to be in the plane, and then there's some modulation in the plane. Then this well-defined group to calculate the energy. And in this case, the gap comes out to be proportional to this bond exchange anisotropy to power. Now, to get a feel for what happens, so if we don't have the exchange anisotropy, the Diffraction relations have important and however, when we add exchange anisotropy, there are only very tiny changes at high energy, close to the boundary here, and the spectrum no longer has 3 folds. For example, if magnetic moment is oriented along the white arrow here, then you get some squeezing of the dispersion. So nodal lines move in. That's illustrated here. The dashed lines correspond to the isotropic XXD model, and then the finite exchange anisotropy shifts this in. So if one was to scan at the nominal key point up in energy, instead of a single mode, one would see two modes. And indeed, that is what we see expressed. So that red line is the expectation of a single peak taking into account instrumental resolution effect, what have you, whereas what we see experimentally is actually fine structure. So looking now at other fine structural details, as I mentioned before, there are special directions on the boundary where we clearly see experimental splitting cannot be explained by the assuming XX anisotropy. However, if we add some exchange anisotropy, then dispersions of different domains, for example, these two up here, which is rotated 120 degrees, actually become different, and this can provide a natural mechanism to explain the splitting here. So one can find a quantitative value for what kind of exchange anisotropy would be compatible with the experiment, and the splitting here and the fine structure decay points can be consistently explained by this magnitude of exchange anisotropy. So by considering this model with exchange anisotropy, we have a minimal model to explain why there is a spectral gap, why we have a fine structure at the key points, and also why there's a splitting on the zone boundary. However, there's a problem that the value that we have to obtain that's constrained by the splitting we observe at the zone boundary predicts a gap that's about factor 5 too small compared to what we see experimentally. So, so this suggests that we have to consider going beyond the lowest doublet. So consider also orbital fluctuations. And you might think that's probably relevant because the orbital excitations are very close nearby here. So the scale of magnetic exchange and the crystal field levels are actually quite close. So first of all, we cross-check that we understand the magnetic moment, so the admixture of spin and orbital parts, the magnetic ground state. So here is a plot of G factors as a function of trigonal splitting. So for cubic anisotropy, G factors for moment in the plane and out of the plane are expected to be the same value, around about 4 1/3. However, if we go into the elongated side, the left-hand side, which is Ising-like, and if we go right, that's the XY-like, around about here, we're giving the transitions to crystal field levels that we've seen experimentally. Now, there's apparently a problem because this can only explain why the magnetic moment of 2.5 Bohr magnetons, whereas experimentally we see 3 Bohr magnetons. However, what we've missed in this picture is the interaction with the neighbor. So if we include the interactions with the neighbors, which we've already determined by fitting the spin revelation, that will lead to a splitting of the lowest Kramer doublet, and we'll remix the wave functions of these levels, and that can produce a much larger moment than the single ion picture. And by putting in the exchange values that we fit from spin wave dispersion, that puts us round about here, which is essentially the same value of 3 Bohr magnetons that what we see experimentally. So this gives us confidence that this is a self-consistency check, that we can explain the magnitude of the ordered moment and the fact that we have easy plane anisotropy within the same Hamiltonian. So here is now a model that we propose can explain all the features that we've seen experimentally. So we work in the basis of the L equals to 1 orbital doublet. And so we have 3 orbital states and 4 spin states. So we have 12 states in total. And then we work with spin orbit coupling, trigonal crystal field. These two together would give us the crystal field splitting that we've already measured. And then we add, in the first approximation, a Heisenberg exchange. And then when this model is projected onto the lowest doublet, this gives us an easy plane XXZ model, which we know is roughly about right to explain the main features apart from the gap and fine structure. Now, the exchange path for edge shared cobalt ions has been looked at by various empirical papers by Leon Kaliulin and Motome as well. And one insight that they proposed is that actually the exchange happens through certain orbitals. For example, terms up here indicate that exchange can happen from the orbital A on this side through oxygen into orbital B on this side. One way to unwavingly think about this is that if the spin flips, then it also changes the orbital. So, by doing a mean field analysis on this main Hamiltonian with spin orbit coupling, trigonal crystal field, Heisenberg exchange, and adding terms like this, which are spin orbital exchange, at the mean field level, this already provides a mechanism for ground state selection and opening a gap. So here is an illustration of the kind of agreement that we get with the data. On the left-hand side, it's a minimal model that contains a ferromagnetic nearest neighbor exchange and some interlayer coupling. This is not a fit. These are just values that are selected to roughly match the experiment. It's a much more involved calculation, so we're not doing the fit 1,000 points as we've done before. But you already see that this captures very well the experiment. The strong modes are strong, weak ones are weak, and so on. And by adding a very small spin orbital exchange, that leads to a finite gap as we see experiment. So in this picture, we can also obtain at the same time the dispersions in the exciton levels, and that's also described very well. For exactly the same exchanges that we use to describe the magnons, we also describe the exciton. And the sign of the topping, why this mode is strong, at the top here, why it's absent here, why there's two modes in this part. All of this is quite well. So as a final point, you may ask, well, you've looked at anisotropy for the effective spin a half. However, the true spin is spin 3/2. So how about anisotropies at this level for spin 3/2? And indeed, in this case, one can have several anisotropic terms. This is the easy plane part. Then the combination of those two can give a Kohn type anisotropy, and the other two can have 3-fold and 6-fold anisotropy. So what's relevant for us is when spins are in the plane, so theta is pi/2, this anisotropy cancels, and this is the relevant term, which is indeed a cosine 6/5, which is what we expect. However, this anisotropy must come from projecting a crystal field Hamiltonian through the spin orbit coupling. And so the relevant term that gives rise to this order 6 anisotropy would be of order 6 in the orbital angular momentum, L plus to the power 6 and L minus to the power 6. But if we're talking about the lowest orbital triplet, L equals to 1 here, so this operator cancels for that level. So we believe it's not applicable here. It reinforces the idea that it's not local anisotropy, but it's in fact interaction that leads to the ground state selection. So just to summarize, how am I doing through time? Anyway, it's my last slide. Yeah. So we've seen a spectral gap, which indicates a discrete set of orientation, which cannot be understood semi-classically. And I've discussed the minimum model based on bond-dependent anisotropy and zero-point fluctuations, which can provide a mechanism for gap opening. So the idea here is that the zero-point fluctuations do select preferentially some spin orientation, whereas classically that cannot be explained. And then I've also described a more comprehensive picture, which involves also the orbital degrees of freedom. And we believe this is more relevant here because magnetic exchange, spin orbit coupling, and trigonal crystal field are all comparable. And in this case, the ground state selection is due to spin orbital exchange. So some spin directions actually gain energy because the orbitals can also gain energy, more energy for that orientation than others. And I've also shown measurements where we revealed the linear band touching and then the intensity asymmetry around these associated with the isospin picture. And you know, these sort of set out some experimental techniques to look at potentially more complex band touchings in other systems. So thank you very much for your attention. Amos? On the single line, it's an interaction that is present all time, but stronger at omega. Yes, yes. So, I think that's what comes from the. I mean, when the electron, I mean, orbital electron, magnetic field. Yes, yes, but at the single ion level, there is. This is all inside the atom. So these are, you know, partially filled shells who have spin orbit coupling. that links up the orientation and together give us the Wundt. Yeah. So it's a basic, many things of spin-off factor and spin half that would solve the problem. However, it cannot provide a mechanism in the strong of the dynamic. So this people mind that the experiment combination of elements. So this finally yes, both all the normalization, everything are captured. But so so we just treat this as Kramer's doublet of not assuming the function form. Oh, sure, sure. I mean, so we have nerve most allowed about none of them. We, are 40 current. Suppose the 3 volts ferromagnet. Yeah. Yes. With possible. Oh, great. Yeah. But the fact was mentioned.
know whether you go. This process broke at light.
So I don't think so far we specific what is right.
Oh, he just that would take it. No.
I could I may have hey Young, this is so some mapping to this extended JK and so on. Yes, yes, I believe we have. Yes. Yes, 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 yeah. Oh no. So I only have this is a movie. Let's see if that works. This is a movie. So the triangle now is triangle. That is working around the but then so yeah. Very naive. Oh yes, yes, yes. So yeah. So yeah, so so I believe that's due to this effect. Once you have, also, the nodal points are not symmetry restricted near the tip. This is a fully 3D structure, and the Brillouin zone actually has facets like this. So if you project the K points, it goes around several facets of the Brillouin zone. There's no need for the nodal lines to be symmetry linked to any point. Maybe you can think of the rhombohedral structure as some sort of threefold screw, but it's not really what you'd call a R3 bar. So yeah, okay, let me go back here. So in this model where constant energy and the model once you have the one anisotropy, point. So for the scaling nominal case here as a gap. Now I say, well, why don't you go there? Two reasons. One, second, there will be another two domains where this is inside the gap. So you're always going to be dominated by two gap modes, unless it's possible to somehow strain the sample and stabilize a single domain. Then we'll be able to look at go at the precise point where we expect a single nodal point. But you know that there's some bond-dependent anisotropy which shifts the location one away from the K point. Once you have the stacking of layers, the Brillouin zone looks like this. Not linked to any special points here. We haven't found a mechanism to open up by any fraction application. A statement that I can make. Maybe there's it's somewhere away from, I mean, the full model is actually that we have yeah. Into so doubling the one top one is doubling the bottom. Now if you got then these two points separate like that, Then these nodal points wind around the double helix as you go up. Yes. Into opposite side. Line. But we don't have the resolution. With infinite resolution, but the experiment. But this will be what's for the double helix line round. Yeah.
Finally said the Magnon problem. Perfect.
Hey.
Yeah, I mean, maybe start. There is tool that delivers a couple almost minus this. There's a couple ferromagnet. Then you have a single move. That will be much further away. So they're happening really binding opposite direction or a line almost find a ferromagnet from chromium bromides. They can't make. So it's probably very like that. Ferromagnet and the diameter appear at first order in here as a ratio. That's why it's J2 is the layers are stuck with the offset. One side that has and if it's Heisenberg-like, then no the lines are exactly the same. However, if this is anisotropic, so has XX part, Z part different, then we get for Heisenberg coupling between node lines are exactly, but for XXZ interlayer coupling, then you get a splitting, which goes the magnitude of Sotro to XX divided by the from the coupling inside it. So the red and the blue have different. So one is there. possibly.
No.
Yes, yes, I
Let's
will.
talk about with
Okay.